Assalamu alaikum. Welcome to lecture number 21 of Digital Signal Processing. In the last lecture, we have covered the topic discrete Fourier transform. In this lecture, we are going to expand our discussion on fast Fourier transform. As you all know, fast Fourier transform is one of the robust and efficient method used to analyze any real-world signal. However, in majority cases, we apply FFT, which is fast Fourier transform, to analyze any signal because it provides us result in lesser computation and in lesser time. So we prefer to apply FFT to analyze any signal. So in this lecture, we will discuss FFT in detail, what this technique is about and how we can compute the frequency spectrum of any signal with the help of fast Fourier transform. So basically FFT is based on DFT analysis and synthesis equation, but what we are doing, as we know that basis function, which is e raised to power minus j 2 pi over n, is a rotating vector. So taking the advantage of this rotating phasor and advantage of its symmetry and periodicity property, as mentioned in this slide, this one is the symmetry property, that is, this phasor will repeat its symmetry after certain time interval, and it is periodic in nature after certain time. So utilizing these two properties, we actually lessen the burden of computation of DFT. So we devise several algorithms to lessen the burden of DFT, and one of the most popular algorithm is FFT, which is fast Fourier transform. There are various versions of fast Fourier transform, such as radix 2 algorithm, radix 4 algorithm. In this lecture, we will cover radix 2 FFT algorithm, as it comes under the scope of our course. So in simpler words, fast Fourier transform is a faster way to compute discrete Fourier transform, and with the help of this technique we can actually perform digital filtering. A question may arise in your mind that why FFT is required. So you can imagine, in standard DFT, as the value of n increases, a large number of computations are required, because number of computation depends upon n square, as we have seen this in the previous slide under the topic of total number of computation. It is directly related to n square. So as the value of n increases, a large number of computations are required. So special algorithms are required to reduce the number of computation. So these type of algorithms are collectively known as fast Fourier transform. So as I told you earlier, there are various algorithms that comes under the category of fast Fourier transform, such as radix 2 algorithm, radix 4 algorithm, and so on. So this is one of the technique which can compute the DFT in lesser time and in less number of computation. You can take the example as given in the bullet point 2. If we take n as 8 here, so you can see that n square is basically 8 square. If we are talking or considering about the standard DFT, then you all know that it depends upon n square. So if the sample length is 8 points, so we have to take 8 point DFT. So there n square is encountered. So 8 square means 64. However, if we divide the points and calculate the DFT of half values first and other half values later on, and then combine the results in some special manner by some algorithm, then you can actually see this formula. If n is divided into two sample sets, then n divided by 2 will become 8 divided by 2 will become 4, and 4 square is 16. And as we are dividing the total number of samples in two sets, then we have to perform the computation for each of the sample set. So it means we have to do the computation two times. So here 2 is multiplied with this factor. So 8 divided by 2 is 4, and 4 square is 16, and 16 multiplied by 2 is 32. So you can notice that here, by using this approach, only 32 computations are required, whereas in the standard form we are needed with 64 computation. And you can imagine we are considering n as 8 here, but in practice our signal has the sample values which has very large number of n or sample points. You can say thousand and hundreds of points. So you can imagine that by applying this approach we can actually save our time and save the number of computations, which basically is the fast Fourier transform. So here in this slide, approach of fast Fourier transform algorithm is explained graphically. You can see the approach of FFT is based on the decomposition of n points DFT into successive smaller point DFTs. You can say suppose we have 8 number of samples in the original signal for which we have to calculate the spectrum. So we have to take 8 point DFT. So you can imagine it is directly related to n square. So total number of computation will be 64. But if you divide this sample set into two sets of equal number, which is 4 and 4, so you can see that 4 square is 16, again 4 square is 16, so 16 plus 16 is 32. So you will require only 32 number of computation if you divide this set into two parts and then take the DFT of each part separately, then combine results with some special arrangement or manner to get the actual answer. Or again, if we are interested in saving more number of computation, then we can actually divide this 4 number of sample into a smaller numbers such as 2 and 2. So you can see that this set is also divided into two sets, each of which contains two samples. So we can calculate the number of computation for this third step or third decimation step. So 2 square is 4 plus 4 plus 4 plus 4. So it will become 16. So total number of computation that will be required after breaking the sample set into two samples, then it will be 16. Or again, we can further decimate it in one sample and take the DFT of single sample and then combine the result. In this way we have only one value, and you know that 1 square is 1. So we have total number of computation is equal to 8 for this stage. So you can see that we are decimating the number of samples, and it depends upon us then how further will go in decimation. And if we go at this stage, because this is the last stage of decimation, after this stage we cannot further break the sample as it is already divided or decimated in single sample. So if we divide the sample set up to this stage, then this approach is the approach of FFT, which is known as full decimation in time, because we are completely decimating our sample values in time to single values. So this is basically divide and conquer approach applied. Here approach of FFT is explained in a different manner. Suppose we want to calculate x of k, which is the frequency domain representation, and we actually divided our sample set into two equal number of samples, which is 4 sample in first set and 4 sample in another set. Then we are taking the DFT for n over 2 values, because in actual set we have 8 values. So we first take DFT of first 4 values, then the other 4 values, then we actually combine the values with some special manner as written in this slide. G of k is the first output and h of k is the output for the second DFT block, and we are combining these two results in a special manner to get the desired result or desired output, which is the frequency domain view of that signal. So you can notice that this basically the spatial structure these lines are forming. So because of this structure, this pattern or this technique is known as, or this shape is known as butterfly structure, because of this very specific pattern of FFT. So we have to apply some mathematical operation on each and every step. And if you zoom in that butterfly structure I told you in the previous slide, then each of this line is basically multiplied with a factor wn, and for the diagonal lines its value is equal to 1, and for the straight lines or line with angle 0 degree it is multiplied with this factor, and if you calculate this factor then it will come out as -1 as simplified in this figure. So this diagonal line is multiplied with +1 and this straight line is multiplied with -1. So here is the basic structure of fast Fourier transform. We will learn more with the help of complete 8-point DFT structure of the same butterfly diagram. By considering we have 8 number of input samples and we have to calculate its frequency spectrum by using this radix 2 full decimation in time algorithm. So we will see this in the later slide. But before proceeding to the actual structure or actual methodology we have to follow for calculating the frequency spectrum, we must know that there must be a special arrangement of input and output. For example, if these values are representing your input, then these values are representing your output, and it is based upon the bit reversal technique. What this slide is explaining you people, suppose you have the sequence or the samples and you denote that sample as x of 0, x of 1, x of 2 till x of 7. Suppose we have 8 number of samples and we are arranging in the ascending order. So if we apply the input in this fashion, Then according to the bit reversal technique, we will get the output which is x of k actually in this pattern. First we will get x of 0, then at the second output stage we will not get x of 1, instead we will get x of 4, then we will get x of 2, then x of 6, x of 1, x of 5, x of 3 and x of 7. And how this is happening, suppose the input pattern is like this, we have to transform it in the binary form. So 0 0 0 is representing x of 0, 0 0 1 is representing x of 1, and similarly for the other values. And we know that we have only 7 values, so we only need 3 bits to represent these values. So the output can be calculated, or how we can tell the corresponding output of x of 7. How we will know that it will be x of 7? We have to read the bits in reverse pattern, that is 1, and 1 is written here, then middle one is written here, and the starting one is written here. So we are reading in this direction from the last digit to the first digit. How we can read this f6? 0 1 1. So if the input is x of 6, then the output frequency content is x of 3, capital X of 3. So I hope you get this concept. If we arrange the input in ascending order, then we will not get the output in the same order, but the output is arranged in a particular manner according to this bit reversal technique. So for our easiness, we usually arrange the input in this pattern, which is the reversed pattern. So at the output we will get the frequency domain contents in ascending order. So we will see it in the later slide also. So here are the values of W calculated for different values of N. If we are taking 2-point DFT, then we will consider N as 2, and two values of W will be computed, that is W20 and W21, which is 1 angle 0 and 1 angle minus 180, which is simply 1 and minus 1. Similarly for 4-point DFT, we have to calculate 4 values, W40, W41, W42 and W43. And if we are calculating 8-point DFT, then we have to calculate these 7 values, these 8 values including 0th value. So these W value will be used in the butterfly structure. So first of all we have to calculate these values, then we will use these values in computation of butterfly diagram, which is in the later slide. So here is the basic structure or the butterfly diagram, which composed of FFT algorithm, very popular algorithm, which is radix 2 algorithm. And radix 2 algorithm is basically that algorithm which is decimated fully in time. If we have 8 samples, then we first divided that samples into 4 number of samples, then 4 again divided into 2 number of samples, then that 2 will further divide into 1 single sample. So we decimate the original signal completely. That's why this is known as radix 2 full decimation in time algorithm. But there is a limitation of this algorithm also, which is, as I said, uh, we are decimating our sample fully in time, so we must have such type of signal which have sample values which can represented as 2 raised to power k. So k where k is any integer. So if you can represent the number of samples which is n in 2 raised to power k, where k is any integer, it means if k is equal to 1, then 2 raised to power 2 raised to power 1 is 1. So you can have two number of samples in the original sample set of provided signal. Or if you are considering k as 3, then 2 raised to power 3 is 2 2s are 4, 4 2s are 8, then n is equal to 8. So it means your original signal must have 8 number of sample values. But again, the sample signal is not always appears in this fashion. It may have some sample values such as 5, which we cannot represent as the power of 2. So what we will do then? So this is the limitation of radix 2 algorithm. However, we can solve this issue with some smart solution. So we have multiple solution for it. Suppose first option is we can only take the consecutive samples which can be represented as the power of 2. For example, if we are provided with 5 samples, so we can represent 4 samples as 2 raised to power 2. So we will take only first 4 samples and discard the fifth sample. But you know that it will degrade the quality of our output as we are omitting our original sample values. So it is a not much efficient technique. Another technique which we can implement for this issue is zero padding. And zero padding is basically the appending number of zeros so that your sample set become equal to 2 raised to power k. So for example, if you have 30 values in the sample set, and you know that you can represent 2 raised to power 5 as 32, so you will append 2 zeros in the original signal. As you know that 0 will not affect the output of your signal, so you can append 2 zeros to make it the equal to sample values equal to 32. So after doing this, you can actually represent 32 as 2 raised to power 5. And as you know that you have appended zeros, last two zeros or starting two zeros, so this will not affect your actual output. So this is the better technique. Coming back to our topic, so what is basically the technique radix to full decimation in time? Please look at this slide very carefully as it is very interesting as well as bit complex. Yeah, so if you lose your attention anywhere in the video lecture, you will not understand this concept very clearly. So be focused while listening this concept. We are arranging first our input values or input samples. As we discussed in the previous slide, we have to arrange input in a particular manner, or either the output should be in a particular manner. So we are more interested that input is shuffled somehow so that you will get the actual output in ascending order. So according to bit reversal technique, first sample value will be x0, second will be x4, third will be x2, fourth will be x6, fifth will be x1, sixth will be x of 5, and the last value will be x of 3. This is in accordance with the bit reversal technique. So as we reversed or shuffled the input sample at the input side, so we will get the frequency output in ascending order, that whatever the output will be, it will follow x of 0, x of 1, x of 2, x of 3, and we do not need to shuffle the output values. But if we do not shuffle at this stage, then we will get output in the shuffle form. So it's better to do it here for easiness. Now please look carefully. The last value is x of 7. I missed that one. So here it will become total 8 number of values. Okay, fine. So I have written all the values. Now, as I told you earlier, whatever will be the output, it will be in the ascending order. So you don't need to arrange the output. As you can see, the first output is x of 0, then x of 1, 2, 3, 4, and so on till x of 7. Now, what we have to do here, we actually have to write the sample value. For example, if we provided x of 0 as 0.1, then we have to write 0.1 here. If x of 4 is 2, then we have to write 2. Whatever the value of samples provided in the signal, we have to write those values in against these values, these notations. So now please look at this slide very carefully. We are actually going to calculate the frequency domain output. First of all, we have to draw straight lines. Then actually, as we are full decimating the signal in time, so we are taking two values DFT first, then after that 4 values DFT, then after that 8 values DFT. So in this stage we are considering only 2 values and will apply some mathematical operation on these 2 values to get some answer, and then we will proceed with that answer to get our final answer. So you can see we actually draw a diagonal arrow here, and the second arrow will be drawn diagonally here. You can see the second arrow is drawn like this. Fine. So this happens with the first 2 values. Now for the next 2 values, you have to repeat the same strategy. First of all, straight lines with the 2 values, then 2 diagonal lines, and please make sure you must mark the direction of arrow very correctly. It is in this direction, you can notice, and the second arrow which is in the upward direction. So in the similar manner you have to perform this for other 2 values. First of all, straight lines, then 2 diagonal lines with proper arrowheads, because these arrowheads will guide us the operation which we have to perform and in which direction we have to move with our results. And again these 2 lines in a straight and the 2 diagonal lines. So here the first structure or first stage is complete, where we are calculating 2-point DFT with each 2 samples. Now please see very carefully. We have to write, as we are taking 2-point DFT, so n is 2, so we have to write W20, and this W20 belongs to this diagonal line. Fine. This diagonal line is representing W20, and if we calculate the value of W20, it will come as 1. So you may write it or you may omit it, but you must know that W20 is multiplied with this line which has the value equal to 1. Now W20 and the second one is W21, and W21 is written on this straight line. Please remember, W20 is written on the diagonal line. Whatever the value of W20, it will be multiplied whatever the value for this line, and W21 is written on the straight line. So one value is, you have to write one value on the diagonal arrow line, and the second W value you have to write on the straight line. And if you calculate the value of W21, then it will come as -1. So actually we have to take -1 as a multiplier for this line. Whatever the values are passing from this line, we have to multiply all these values with -1. Now same procedure with the second stage or second set of first stage. As this is the first stage, W20 is written on the diagonal line and W21 is written on the straight line. Please see the position of W20 and W21. You have to write it very carefully. W21 is indicated as -1. Similarly with the third sample set of first stage, W20 and W21, and similar with the last sample set. And for your convenience, you may mark this intermediate output as A0, A1, A2, A3, A4, A5, A6 and A7. Now how you will calculate A0? You will see that A0 is the combination of x of 0 plus the value coming from this arrow, which is x of 4. So which is multiplied with W20. So A of 0 is actually x0 plus x4 multiplied by W2. I am again repeating, A of 0 is equal to x of 0 and x of 4 multiplied with W20. Similarly, A1 is equal to, you have to see, A1 is equal to x4 multiplied with -1 and plus x of 0, because two arrows are merging to form A1. So A1 is equal to x of 4 multiplied with -1 plus x of 0. So similarly, you can calculate for A2, A3, A4, A5, A6 and A7. For example, for A6 and A7, I am again repeating the concept. A6 is equal to x of 3. Whatever the value of x of 3, you have to add up this value with x of 7 after multiplying x of 7 with W20, which is 1 in this case. So A6 is equal to x of 3 plus x of 7 multiplied with W0. And what about A7? A7 is equal to x3 plus the product of x of 7 with W21, which is -1. So here we are getting the intermediate output, which we are representing with A0 to A7, and it is the first stage output.